Hi dear students, welcome to Gate Wallah. This is Satish Kumar Durishetty, Faculty of Measurements and Instruments. Welcome to the lecture 2 of one-shot series of electrical measurements, which is a common subject for both electrical engineering and instrumentation engineering students. Last lecture we have discussed about bridges. In the bridges, DC bridges, AC bridges, in one short lecture I have given you some model problems on Wheatstone bridge and some theoretical questions on AC bridges. After thorough completion of the bridges, now we are moving to the next chapter, that is error analysis. Error analysis is one of the important topic with respect to gate EE and instrumentation measurements, because every instrument whichever you are used in our day-to-day life definitely will encounter an error. These errors may be due to the problems by the manufacturer, or these errors may be due to the usage of the consumer, usage of the person, and these errors and also may be because of environmental issues. So based upon the situations, these errors are classified. These errors are classified, and all that classification of errors, and especially in gate, what are the different model problems? Around 10 to 13 model problems I am going to cover in this one shot series. Okay, so all of you, please open your book and pen and be ready. And I always mention, you must carry a notebook while you are listening this YouTube lecture. Even though it is a YouTube lecture, you have to feel it as a live session so that you will be in tune with my lecture. Okay, chal. In this lecture of error analysis, the topics that I am going to discuss, first topics I am going to discuss is types of errors. Of course, it is a theoretical topic. But the students may be aware of these particular errors. With respect to gate and with respect to non-gate, it is very important to have an idea of types of errors. Why? Because sometimes in the gate exam and non-gate exams, theoretical questions are asked on the errors. Second thing, guaranteed accuracy error, which is the most important. These two, guaranteed accuracy error and limiting error. If you open the previous year gate papers, number of times the questions are asked on guaranteed accuracy error and limiting error. And finally, number of numericals I am going to discuss, maximum different model problems I am going to discuss. Next comes the uncertainty error. Uncertainty error is also one of the important error in recent exams. Recent papers, the questions are asked on uncertainty. First of all, what is error? I think all of you know, error means fundamentally what? Error means measurement value minus true value. In short, you want to measure certain parameter by using a voltmeter, you want to measure the voltage. The actual voltage is 5 volts, but by using this instrument, you are getting as 4.5 volts. So measurement value minus true. That is the error. And what is the correction factor? Correction factor will be negative of error. Correction factor is the negative of error. So error can be plus or minus, correction factor also can be plus or minus, in simple words. But the types of errors, theoretical hai, there are 3 types of errors. One is called gross error. Second one is called systematic errors. Third one is called random errors. Second. Hello, yeah, sorry. One is called the gross error, second one is called the systematic errors, third one is called random errors. So which are gross error, which are systematic error, which are random errors? Don't think it is a theoretical topic, we'll skip. But on this also, recently in some of the papers, latest gate papers, we are getting questions. That's why I have added this, and you should have some basic idea. If you want to enter into the problems, just wait for some more time, matter of 10 to 15 minutes. First, let me complete this theoretical explanation, then we'll move to the error. Okay, so errors are broadly classified like this. This simple diagram, this particular single diagram will give you the complete history of errors. So errors are broadly classified as gross error, systematic error, and random error. Gross error, systematic error, random error. Systematic error is again classified into 3 categories: instrumental errors, environmental errors, observational errors. Next, Instrumental errors are again classified into three things: loading effect related, misuse of instruments, inherent shortcomings of instrument. Sir, what is this, sir? How to understand? I will explain in brief one by one. First of all, what is gross error? Let me talk about gross errors. Generally, when you are using the instrument, human beings are having certain tendency in connecting the instruments, or in reading, in taking the readings of the instrument, or taking the recording of the readings. There is a possibility of committing a mistake. So in brief, gross errors are majorly due to the human mistakes. In short words, I am telling, these are coming due to the human mistakes. Human mistakes in connecting the instruments, reading the readings, and recording the values. So all those errors will be called as gross errors. And what is the remedy to come out of this gross error? What is the technique to come out of this gross error? There is no other technique. So the humans must be very careful. While you're connecting the potentiometer battery, while you're connecting the megger to the high resistance measurement, while you're connecting the galvanometer to the Wheatstone bridge, you should be very, very careful. So the only rectification for this gross error is human beings must be very careful. That's it. So that's all about the gross error. Okay, I'm not entering much to the theory, because on errors we are getting more as numerical problems, but as in brief I'm giving this. Gross errors are majorly due to the human mistakes. Next comes what? Next comes systematic errors. The systematic errors is due to the instruments, due to the environment, due to the observation. So as I told you, these are having many possibilities. Instrumental errors. Instrumental errors means what? Let me talk about here in the classification. I will show you. Instrumental here, loading effect. One of the important hai, loading effect. What is loading effect? So when you are connecting a meter, obviously, so this is our measurement. Suppose there is a simple voltage division circuit. So here there is a resistor R1 and this is a resistor R2, my dear. So this is, let us take 5 volts. Let us take this is 100 ohms. Let us take this is 100 ohms. And what should be the ideal voltage that I have to get here? If you take the ideal voltage across the second resistor, the second resistor should be how much? So that is voltage division rule. If you apply 100 by 100 plus 100 into 5, so you should get a 2.5 volts. So this 2.5 volts is the true value. Yes or not? But when it comes to the practical, you are going to attach the meter, right? So to measure this particular, what you are going to do? You are going to attach a meter. When you are attaching a meter, my dear, so what happens? The meter resistance comes into picture. So when meter resistance comes into picture, this 100 ohms and this meter resistance will be in parallel. Definitely whatever that you are going to get, that is definitely V meter measurement. So this will be lesser than 2.5 value. So this is due to what? Loading effect. Loading effect is compulsory, not possible to eliminate. We cannot eliminate the loading effect 100%. Okay. If you want to eliminate the loading error, definitely what happened? This meter resistance must be infinite. Is it possible to get infinite resistance? No. Okay. So that is the point you have to understand here. So these are instrumental related errors. Each and every instrument is having certain shortcomings. For example, see this, if you see this particular table, if you see this particular classification, inherent shortcomings. The loading effect is due to what? Meter resistance never is possible to have infinite. So this is due to meter resistance. Meter resistance is finite. So this finite meter resistance, when you attach to another resistor, definitely as a parallel combination, there we are going to get some extra drop in the voltage. So this drop in the voltage will reflect in the true value, in the reduction of. Next comes the misuse of instruments. Suppose you are using a DC instrument for AC measurement, or for AC instrument DC measurement. So this confusion, DC to AC confusion may be you are going to get errors. Next thing, inherent shortcomings. Inherent shortcomings means what? For example, PMMC is there. For example, PMMC. I think PMMC everybody knows now. In next coming chapters, we are going to discuss, the next coming lectures, we are going to discuss the measuring instrument. So in PMMC, we are having the spring, right? I think all of you know there is a spindle. For the spindle, there are two springs, control springs. And this particular control spring, definitely what happens if you are going on using for years, it loses aging effect. Yes or not? Due to what happened, due to age, there is an effect. There is a reduction in its stiffness. And even the magnetic strength. So many instruments like moving iron, dynamometer, they are using the magnets. When you are using for decades, or when you are using for 20 or 30 or 10, 15 years, what happens? The frictional properties, the mechanical properties of those devices will going to be affected. So because of that, what happened? The instrumental lifetime is going to be affected. So these all will come under instrumental errors. Next, environmental errors. This is not in the control of the human beings. This is not in the control of the instruments. Environmental errors like temperature, humidity, pressure of the atmosphere, they will affect definitely whatever the meters that we are using. All those meters are having internal resistance. That internal resistance of the meter is manufactured by what? It is manufactured by a copper, a metal. The metal is having a positive temperature coefficient of resistance. As the ambient temperature is changing, its resistance is going to be affected. So that is the environmental. Observational errors, observing the connectivity observations. The most important is a random error. The next important is a random error. What is random error? Any idea? So random error is no reason. We can't say no reason. Whatever may be you cannot explain the reason. This is what we call as universal error. What we call it as universal error. You cannot define, can't be defined the reason. Can't be defined. Very interesting. You can say God's act of God. Can't be defined as, can't be defined a reason. Can't be defined a reason. You can say act of God. In simple words, you can say act of. However, the care you take, whatever the 100% accuracy related things you have done, but still there is a possibility of getting an error. And if you do research, what is the reason behind this error? You are not going to get an answer. So such situations, that error is called random error. So this is a brief idea. I think all of you got the clarity about the errors. Errors are classified as gross errors, systematic errors, random errors. Gross errors are due to human mistakes. Systematic errors are due to instrumental, observational and environmental. Random errors, no reason, universal error, whatever the care you take. Okay, let us move this. Let us cover this theoretical topic. Next comes the guaranteed accuracy error. Very, very important error, my dear. On this, we are going to have the questions. What is guaranteed accuracy? First of all, what is accuracy? So, what is accuracy, dear? What is accuracy? So, this accuracy is called closeness to the true value. Accuracy is closeness to the true value. Guaranteed accuracy error means whatever may be the care you take, there is an error is guaranteed. Okay, there is an error compulsory guaranteed. What is that guaranteed error? See, when accuracy is expressed in terms of error, it is called percentage guaranteed accuracy. See, actually accuracy means closeness to the true value. How it is expressed? It is expressed in terms of error. When it is expressed in terms of error, when accuracy is expressed in terms of error, it is called guaranteed accuracy error. And always remember, this guaranteed accuracy error is always with respect to full scale value. Is always with respect to full scale value. And remember, it is always fixed. It is always fixed. It is always fixed, and it is fixed by the manufacturer. The manufacturer will tell, when by using this instrument, if you are measuring the full scale value, if you are measuring the full scale value, there is a guaranteed error of 1% or 2%. Okay, so how to understand this? Let me explain you like this. If you take a meter, for example, this is a voltmeter. Let us take this is 0 to 150 volts is the full scale value. So the manufacturer has given the percentage of guaranteed accuracy error. See the full form. Guaranteed accuracy error is given as 2%, plus or minus 2%. 2% of guaranteed accuracy error. So 2% of guaranteed accuracy error means what? 2% of full scale value. That means what? 2%. 2 by 100 into 150. 2 by 100 into 150. So that will be how much? 3 volts. 3 volts. Percentage of guaranteed accuracy error is 3 volts. That means when you are measuring the full scale value, definitely you are going to get an error of how much? 2%. 2 by 100 of 150. 2 by 100 of 150. That means 3 volts. So at full scale measurement, this will be how much? 150 plus or minus 3. That means you are going to get either 147 or 153. You understand? This much error is guaranteed. This much error is 100% guaranteed. Okay, na? Whatever may be the care you take, but you are going to have an error of plus or minus 3. But remember, when this error will come, when you are going for the full scale value, always with respect to full scale, that is the point you have to understand. The guaranteed accuracy error is always expressed with reference to scale value. It is given by the man. 3 important points. That's what he has given. It is given always by the manufacturer. Each and every voltmeter manufacturer will have his own guaranteed accuracy error, and it is always fixed because it is talking about what? It is talking about the full scale value when you measure the full scale value. Okay, na? So that is fixed, and it is expressed with reference to the full scale value. It is fixed. Understood here? So one more thing I want to tell you. For example, if you are taking suppose a ammeter 0 to 10 amperes, okay, 0 to 10 amperes, it is having guaranteed accuracy error of 1%. Guarantee accuracy of 1%. They won't mention the full scale value. They will mention the guaranteed accuracy of 1%. Once it is mentioned, 1% means it is by default, it is reference to with respect to full. By default, guaranteed accuracy error is by default with reference to full scale. 1% of full scale value means what? 1 by 100 of full scale value. What is the full scale value? That is 10. So this 10 is nothing but 0.1 plus or minus. Means by using this meter, if I am measuring 10 amperes of current, I am not going to get 10 amperes. Definitely 100% a guaranteed 0.1 error is going to come. Either 9.9 I will get or 10.1 I will get. So that is guaranteed. Okay, na? Now, by using this instrument, if you are measuring other than full scale value, then what happens? Definitely the error changes. Okay, so by using this particular meters which are having certain guaranteed accuracy error, if we are measuring other than the full scale value or including the full scale value, then definitely one more error is coming now. So that error is called limiting error. What we call that error as? That error is called limiting error. The error limited for user measurement by you. For example, if I am taking a meter of suppose 100 volts, the guaranteed accuracy error is suppose 2%. That means what? 2% of 100 volts. That means what? 2 volts. Now by using this instrument, if I am measuring a measurement of 10 volts, if I am measuring a measurement of how much? 10 volts. If I am measuring a measurement of 10 volts, okay, then that means what? You are limiting. You are not going to the full scale where you are limiting to a value of how much? 10 volts. So for measurement of 10 volts, for measurement of 10 volts, the error is what? Okay, so this is 2 volts, but now for the measurement of 10 volts you want, so 2 volts divided by 10 volts into 100%, so that is going to come as 200 by 10, 20%. 20% of what? 10 volts. 20% of 10 volts means, so this is what we call as percentage of limiting error. What we call this as? Percentage of limiting error is coming as 20%. 20% of what? 20% of your measurement. So 20% of your measurement means what? 20 by 100 of your measurement is how much? 10. That is again coming as 2 volts. Have you observed? The limiting error is same. So this is what we call as limiting error. This is what we call as percentage limiting error. So the limiting error, the error is limited here. Error cannot exceed more than this. Okay. So this is what we call as limiting error. Okay. Are you understanding? A meter is there which is having a guaranteed accuracy error of 2%. 2% of full scale value, that is coming as 2 volts. With that meter, if you are measuring a non-full scale value with a measurement of 10 volts, the error is this. Okay. So now with the same instrument, suppose if you see for one second, for a measurement of 10 volts, the error is how much? 2 volts by 10 volts, that is 20%. This 20% is called the limiting error percentage. Percentage of limiting error, 20%. Okay. When you are measuring 10 volts, you will be having an error of 20%. 20% of 10 volts will be equal to again 2 volts, which is nothing but guaranteed accuracy. So every time the limiting error is fixed, but the percentage of limiting error goes on changing. For example, the same thing let us take. This is 100 volts, which is having the 2% guaranteed accuracy error. Now I want to measure 20 volts. Okay. So guaranteed accuracy error is how much here? Guaranteed accuracy is 2%. 2% of full scale value. That is how much percent? Yes, 2%. 2% of full scale value, 2 by 100 into 100. So that means this is what we call error is limited to 2 volts. Now for measurement of 20 volts, for measurement of 20 volts, how much? That will be, you are limiting the error for a measurement of 20 volts. So that is coming as how much, my dear? 10%. Coming as how much? 10%. So 10% of your measurement, 10% of your measurement is 10% of 20. That means 10 by 100 of 20. If you check this, again the value is 2. So have you observed? The limiting error, which is limited always with reference to your. So this is the limiting error. And this is the percentage of limiting error. Understood? Similarly here also, this is the limiting error and this is the percentage of limiting error. If you observe, the limiting error remains constant. The guaranteed accuracy error remains constant. That is nothing but when you are expressing with reference to full scale, same yaar. Guaranteed accuracy error and limiting error words are same. But when you are expressing with reference to full scale value, it is called guaranteed accuracy error. When you are referencing to non-full scale value, it is called limiting error. But the point is, percentage of limiting error is not same. If you are measuring 10 volts, if you are measuring 20 volts, if you are measuring 30 volts, you are measuring 50 volts, 80 volts, 100 volts, then what happens? The guaranteed accuracy error will be same. Percentage of limiting error will be varying, but the limiting error remains constant. Limiting error remains. Okay. So Let me write some conclusions here. What are the conclusions here? Percentage of guaranteed accuracy error is always fixed given by the manufacturer next. Percentage of guaranteed accuracy error is always with reference to full scale value. Limiting error is fixed. Percentage of limiting error is variable. Understand? Limiting error and guaranteed accuracy are almost the words are same, but guaranteed accuracy is the word specifically given when you are measuring for the full scale. You know? So these are some important points, basic points: guaranteed accuracy error, limiting error, percentage of limiting error. Percentage of limiting error is variable, limiting error is fixed. So to get understand of these particular concepts, you have to do some problems. If you do more problems, more clarity you are going to get. Okay, chalo. Now we'll move for good number of problems on guaranteed accuracy. Now we'll start some numerical problems on errors. Till now we have seen the fundamentals of error analysis, types of errors. Okay, now we'll discuss how to solve certain problems. So this is one question asked in GATE 2015, one of the previous year's question. So let us see this question and let us analyze how to do it. 4 independent observations recorded in voltage measurement of 110.02 volts, 110.11 volts, 110.08 volts, 110.03 volts. The average range of error will be. That is a question they're asking. What is the average range of error? So the average range of error, what is average range of error? So that is given as maximum average error plus minimum average error divided by, that is a formula. Okay, so that is the formula. So in errors, you have to use these formulas. The average range of error is equal to maximum average range error plus minimum average range error divided by 2. So now, first of all, let us write the values 110.02, 11. So let us take the average. So what is the average? The average voltage, I can take it as 110.02 plus 110.11 plus 110.08 plus 110.03. Okay, divided by 1, 2, 3, 4 divided by 4. That is the average. Okay, so now if you take the average, how much we are getting? 110.02 plus 110.11 plus 110.08 plus 110.03 divided by 4. So it is coming around 110. So this is the average voltage. Average voltage divided by the. Okay. So now from this, what I want to get here, if you see the list, so we are having a minimum voltage of how much? The list, if you check, what is the minimum voltage? The minimum voltage is 110.02 volts. The minimum voltage is 110.02 volt, and the maximum voltage maximum voltage is 110.11. Okay, so E average is greater than the E minimum. Please make a note this point. E average will be greater definitely than minimum voltage, and E average will be lesser. Okay, so now from this I can get the maximum average range error. So first I have to get the maximum average range error. Maximum range error. So what is the maximum range error? That is E maximum minus E average. E maximum minus E average. So what is the E maximum? The E maximum is 110.11. So 110.11 minus. So what is the E average? E average is 110.06. Times matters. So 6. So we are going to get 110.011. 110.11 minus 110.06 dear. So it is coming around 0.05 volts. Coming as point. Okay, next. E average minus E minimum. So that is going to be the minimum range error. Range. Okay, that will be what? So average is 110.06, minimum value is 110.02. So 110.0 minus 110.2, that is coming as 0. So this is the maximum range error in the list, and below is the minimum range. Now we can find out the average range error. The average range error in the voltage. Average range error in the voltage is given as, so maximum range error 1, take this 1 and 2. Okay, so the average range error will be the average of these two, 1 plus 2 by, so how much we are going to get? 0.05. 0.05 plus 0.04, that is coming around 0. Plus or minus, we take 0.0. What is the answer exactly? 0.0. Now it will point. Perfect. Option C will be the. Okay. So try to understand. In the given list, from the given list, first we have to calculate the average voltage. Definitely, comparatively average voltage, there will be a minimum voltage and there will be a maximum voltage. Take the difference of that. You are going to get the maximum range error and minimum range error. The average of maximum range error and minimum range error will give you the average range error. Expected question last in given field. Okay, please take note of the formula. It according to that formula you can practice. Now let us move for the next question. Yeah, question number 2. The percentage limiting error in the case of an instrument reading of 8.3 volts with a 0 to 150 volts voltmeter having a guaranteed accuracy of 1% full scale. So just before only we have discussed what is a guaranteed accuracy error, what is the limiting error. Okay, guaranteed accuracy error is always expressed with reference to what? Full scale value. Okay, so first of all, what is the range of the instrument? So he has given the options. Options are very close, so it should be very clear, and this is a question asked in the oldest gate 1990. Okay, so now if you take the 0 to 150 voltmeters, this is our 0 to 150 volts. Okay, 0 to 150 voltmeters, and the guaranteed accuracy error is given as, how much? Guaranteed accuracy error is as 1% of full scale value. Okay, guaranteed accuracy is given as 1% of the full scale. So that is 1% means 1 by 100 of full scale value. Full scale value is how much? 150. So that is coming as plus or minus 1.5. Plus or minus 1.5. We can also call it as limiting error. The question asked here is the percentage limiting error. So what is the percentage limiting error? When the error is going to be limited for your measurement. When you are measuring the full scale value, you are going to have, this particular instrument is going to have a guaranteed error of how much? 1.5. That means when you measure the full scale value 150 volts, this instrument is not going to give you 150 volts. The instrument will give you either 150 plus or minus 1.5 volts. Okay. Now, by using that instrument, by using this instrument which is having a plus or minus 1.5 volts as a limiting error, what is the percentage of limiting error for calculation of 8.3 volts? Okay. So percentage of limiting error, how to calculate? Percentage of limiting error is for how much reading it is. The reading that he is going to take is 8.3 volts. So his reading is 8.3 volts. So this instrument for 8.3 volts, how much? Okay. So the error is limited for 8.3. That is a true value. So this is the error with respect to the present true value is how much? That to be measured is 8.3. What is the, how much here? Check it. So 1.5 divided by 8.3 to 100, you are going to get it as 18.07. You are going to get how much? 18.07%. But remember, this is a percentage of limiting error. 18.07% of what? 18.07% of 8.3. So if you take 18.07% of 8.3 volts, how much you are going to get? You can check it. 18.07 of 8.3 divided by 100. So that will be coming around 1.5 plus or minus 1.5. You understand? That is what I want to say. The limiting error remains the same. The limiting error remains the same, but the percentage of limiting error gets changed. So please make a note. Always remember the limiting error. The limiting error remains same. But the percentage of limiting error varies. Okay, so please remember this logic statement. Limiting error always remains same. If suppose you are measuring by using this instrument, you are measuring 10 volts, 100 volts, 50 volts, the limiting error remains same, but the percentage of limiting gets affected. Okay, so this type of questions are repeatedly asked, not only GATE 93, regularly one question is asked. He is giving the guaranteed accuracy error, and from the guaranteed accuracy error, he will be asking you to calculate some limit. Always remember, guaranteed accuracy error is fixed, and guaranteed accuracy is always with reference to the full scale value. Whereas limiting error, percentage of limiting error is variable, but whereas limiting error remains constant. Okay, guaranteed accuracy error is always with respect to full scale value, and limiting error can be with reference to your measurement value. Okay. Now let us move for the going in a sequence. Question we have solved. Question number 1 we have solved on the range of error. Now we are going to solve this, the percentage. Yeah, this question number 3 from IIT Delhi 1992 on the error analysis. Somewhat looks big, but please go through. I think it is visible to you. Okay, clearly it is visible to you. Yes, question number 3. A resistance is measured. A resistance is measured by the voltmeter ammeter method employing a DC excitation and a voltmeter of very high resistance connected directly across the unknown. So I think all of you are aware resistance measurement can be done with VI method. Yes or not? Voltmeter ammeter method. So if you want to know the unknown resistance across that particular resistance, keep a voltmeter and in series with that resistance you keep a ammeter, then you can take the reading of the voltmeter and ammeter reading, and resistance is equal to V by I. So that is a fundamental basic concept everybody has to know. So the R is taken as the voltmeter reading and the ammeter reading. Okay, so if the voltmeter and ammeter readings are subjected to maximum possible errors of plus or minus 2.4% and plus or minus 1.0% respectively. So this voltmeter is having error of how much? Plus or minus 2.4%, and ammeter is going to have an error of plus or minus 1.0%. So if you see, this is the combination of quantities as division. Yes or not? As already in the previous just before lecture I have explained you sum of combination of quantities and product of combination of quantities. Division of quantities or product of quantities, when you are taking, their percentage errors can be added. Okay, so in this picture, so this is our resistance dear. So for this particular resistance there is a ammeter connected, and for this in parallel, so in parallel we are connecting the voltmeter. Okay, so the voltmeter reading, so these are R and V, and now the current passing here, R is equal to V by A. The point here is the percentage error in the voltmeter is plus or minus 2.4% percentage error, and this is plus or minus 1%. So what is the percentage error in R? So that can be taken as summation of quantity, 2.4 plus 1. So that is going to come as plus or minus 3.4%. The right answer goes for this question as, so this is the option D. Like this, every year we are getting one question on the errors, either in terms of the calculation of the percentage of limiting error, or sum of the quantities, or division of the quantities and product of the quantities, or parallel resistors. For instrumentation students, it can be framed a question in terms of some instrumentation transducers, pressure measurement. Okay, if you take P is equal to rho GH, there is an error in the measurement of H, then calculate the error in the pressure, like that. But the matter is, concept is same, only the formulas are changing. For instrumentation student, non-electrical measurements errors. For electrical students, in meters they will be. Question is looking lengthy, but the tricky is when you are taking the product of quantities, or when you are taking the division of quantities, the resultant percentage error is equal to summation of their individual errors. Please make a note of this point. For product or division of quantities, the percentage error is equal to summation of sum of individual percentage. So please, that is already in the before lecture, just before we have seen. Now let us move for the next question. I think all of you are following, right? This question is somewhat tricky. This was asked, very old question, IIT Kharagpur, 1994. It was a theoretical conceptual question. A precise measurement guarantees accuracy of the measured quantity. Is it right or not? How to understand this precise measurement? So what do you mean by precision? First of all, what do you mean by accuracy? Okay, a precise measurement guarantees accuracy of the measured quantity, or we can say vice versa, a accurate measurement guarantees the precise. So what does it mean? So first of all, what is accuracy? Short, I will talk. What is accuracy? Accuracy means it is the closeness to the true value. Is accuracy the closeness to the true value? How far it is close? Degree of closeness to the true value. Suppose the temperature reading is 25 degrees Celsius, the thermometer is showing 24.5, that means the accuracy is plus or minus 0.5. It is 0.5 close. But precision is different. Precision is called as a measure of repeatability. What is precision? Precision is taken as is the measure of repeatability. Is the measure of repeatability. The measure of repeatability. Try to understand, it is a measure of. It does not mean it should be true, but it is the ability to repeat the same value. Okay, see, for example, 25 degrees Celsius is the temperature. So for example, true value of temperature is 25 degrees Celsius. So you are doing an experiment with the thermometer and you are measuring, and the reading one, the first reading T1, you got it as 24.4 degrees Celsius. Is it a true value? No, it is a measurement value. It is 0.6 degrees Celsius away. But the next reading, when you are measuring the same, another student is reading the thermometer. So this time it is showing as 24.39. And if you see, okay, this is very close now. I will take like 20.4. Very not accurate, right? It's not accurate because it's very far. The readings are not accurate. 20.4 means almost 5 degrees Celsius away from the true value. So they're not accurate. But if you see the readings, dear, if you see the readings, they are very, very close. Got it? So they are very, very close. They are not true. With respect to the true value, they are not true. But if you see their values, 20.4, 20.39, 20.41, 20.38, they are very, very close. So they are precise. Okay. So these are highly precise, but are they accurate? Highly precise. They are very close to each other. Highly precise, but no accurate. So highly precise does not mean high accuracy. A precise measurement guarantees, no, it cannot be guaranteed. Precise means ability to repeat the same value, but the same value does not mean the true value. What was my true value? My true value was 25 degrees Celsius, dear. Okay, true value is 25 degrees Celsius. Okay, but the reverse is true. What is the reverse? Reverse. Oh. See the reverse. Suppose the reverse means if you take true value is 25 degrees Celsius and you are doing the measurement, you are getting an accurate every time the student is doing the experiment. First student got 24.89 degrees Celsius. Second student got 24.9 degrees Celsius. Third student got 24.91 degrees Celsius. Fourth student got 24.901 degrees Celsius. You say they are very accurate or not? Yes. They are accurate at the same time. If you see, automatically they are precise. When they are very much accurate towards the closeness to the true value, automatically they are okay. So this is highly accurate. Highly accurate automatically means what? And also highly precise. Highly accurate means highly. Please make a note of this point. Okay. So highly accurate means highly precise. Highly precise does not mean highly accurate. So these are the points you have to understand. Okay. So in the question, what is given? And gone. Here. Yeah. A precise measurement guarantees accuracy of the measured quantity. It's false. Yes or not? You understand? So I will write a statement here. Okay, let me write a statement. See, these all notes will be available to you. Whatever I am teaching, that PDF is also shared by the respective team of the GATE Wallah. So don't worry about that. Just focus. Okay. A highly precise, a highly accurate instrument is precise. You understand? A highly accurate measurement, we can say measurement, not instrument, we can say the measurement, because characteristics of measurement. A highly accurate measurement is also highly precise, but a highly precise measurement is not accurate. not highly accurate, not highly, understand? A highly accurate measurement is precise, but a highly precise measurement is not highly accurate. So what I want to say, a highly accurate measurement guarantees high precision, but a high precision may not guarantee the highly accurate. That is a point. Please make a note of this point. And already I have given you the clarity explanation. I have given a clarity explanation. Accuracy means the closeness to the true value. So it is the measurement of repeatability. Highly repeatable instrument may not be accurate, but a highly accurate instrument is automatically repeatable. That is also one statement you can write. A highly repeatable instrument may not be accurate, but a highly accurate instrument is always repeatable. So this question, very, very good question. False statement. A precise measurement guarantees accuracy. No, accuracy guarantees precision. Okay, so this is the fundamental difference between the accuracy and precision. Especially this is important characteristic. That is what we have to study in the beginning of the instrument, the static characteristics of instrument. Accuracy, precision, what is the difference? Threshold and resolution, what is the difference? Okay, span and range, what is the difference? Sensitivity, transfer function, what is the difference? Okay, repeatability and reproducibility, what is the difference? So we should, especially these type of questions are also asked when you're going for the interview. Accuracy, precision, threshold, resolution, range, span, repeatability, reproducibility. Okay, now, so these all are static characteristics of the instrument, whereas transfer function, fidelity, okay, Laplace transform transfer function y of s by x of s, and fidelity, these dynamic characteristics. Okay, so this question is reflecting the fundamentals of instrument. Hope all of you following. Okay, let us go for the this is somewhat length. Go through this question, check. So we will go for this question. What is this question? Question number 5. I think it is visible to you clearly. This question was asked in IIT Kanpur 1995. See, all are quality previous year questions, dear. Whatever we are discussing, these all are previous year questions. Whatever the questions that we are discussing, these all are PYQs. 4 ammeters M1, M2, M3, M4 with the following specifications are available. So there are 4 meters M1, M2, M3, M4. Okay. Yeah. So he has given the full scale value for the first meter 3.5 digital dual scope. The full scale value is 20 and accuracy is plus or minus 0.1%. And M2 instrument is PMMC. Full scale value is 10 and accuracy is plus or minus 0.2%. And M3 is electrodynamic dynamometer and the full scale value is 5 and plus or minus 0.5 is the accuracy moving errand. Okay, here accuracy plus or accuracy percentage of full scale means what? So he is expressing the accuracy with reference to full scale value, means this is the percentage of guaranteed accuracy. So he has given in the question for each instrument what is the percentage of guaranteed accuracy given. So M1 is having 0.1% of guaranteed accuracy error, M2 is having 0.2%, M3 is having 0.5%, M4 is having 1%, and the full scale values are given. But what actually you want to do, he want to measure a current of 1 ampere. For measurement to be done is current of 1 ampere. So to obtain the minimum error, which instrument he has to choose? So out of all these 4 instruments which are having this respective percentage of guaranteed accuracy error, now which instrument if I use for a measurement of 1 ampere, I am going to get the least error. How to solve this problem? So first let me take the 4 meters. So roughly I am taking the 4 meters here. Okay, so I am taking the 4 meters. So this is 1 and this is 2, meter 3. Okay, yes, 4. Perfect. So this is meter 1, this is meter 2, this is meter 3. First of all, let us take the data what is given. First of all, what is the full scale value of meter 1? That is 20. So the full scale value of the amperes. Okay, na? And what is the full scale 20 amperes. So this is full scale value 20 ampere. This is 10 amperes. What? This is 10 amperes, dear. Ampere, 10 amperes, and 5 amperes and 1 ampere. Okay, 5 ampere, 1 ampere. Last instrument full scale value. So this is what value? This is the full scale value. So we can take as scale value. Okay, and now first instrument guaranteed accuracy is how much? 0.1%. The first instrument guaranteed accuracy is percentage of guaranteed accuracy is plus or minus 0.1 percentage of scale value. So if you take that 0.1 divided by 100, and what is the full scale value here? 20. So if you take, how much you are going to get? 0.1% now. 0.1% of 20. 1 by 1000. So you are going to get 0.02, right? 0.2. This is the limiting error. Now, with this instrument, if I am measuring with this instrument, suppose with this instrument, if I am measuring a current of how much? 1 ampere. Now, for a current of 1 ampere, what is the percentage of limiting error for measurement of? Is the color is okay? I will change the color. I think this is okay, no problem. Percentage of limiting error for measurement of 1 ampere. How to do it? What is the error limited for measurement of 1 ampere with respect to? You have to measure for 1 ampere, right? 2.2 divided by 1 ampere to 100. So you are going to get 2% or minus 2%. This first instance. Okay. I will do one thing here, affecting our board. Just a minute. Testing this. So now I am taking the percentage of limiting error for measurement of 1 ampere. Your limiting error is 0.02. Yes, your limiting error is 0.02 for the measurement of 1 ampere. So for the measurement of 1 ampere, 100 as what is the limiting error? Percentage of limiting error is 2%. Now let us go for the beta 2. Sorry. Let us go for the last is 4. Okay. Now first, what is this information given here? What is information here? Beta 2 is having 10 amperes is the full scale value, and what is the guaranteed accuracy error? The guaranteed accuracy error for the second instrument is given second, that is 0.2%. Okay, so this is plus or minus 0.2%. Okay, so that means I can take 0.2 by 100 to full scale value, that is full scale value is 10. So again you are going to get the same by 1000 at 0.2. Okay, so now this instrument is also for measurement of 1 ampere. Okay, so the instrument which is having a limiting error of 0.02, if it is used for a measurement of 1 ampere, okay, so for measurement of 1 ampere, what is the error? So that is 0.02 by 1 ampere into 100. That is again, so both the instruments are having the same error. First instrument is having 2%. So right here, error I am going to get here much. This is getting 2%. This is also 2%. Go for the other third instrument. The guaranteed accuracy error is given as how much? Let me take the guaranteed accuracy error. The guaranteed accuracy error for the third instrument is given as how much? That means the error which is guaranteed with reference to always full scale value. For the third instrument, the full scale value is 5. and the accuracy, guaranteed accuracy is 0.5%. So 0.5%, plus or minus 0.5%. Let me take the reading. 0.5% of full scale value. What is the full scale value? That is 5. So that is 5 by 10. So 25 by 1000. 25 by 1000 is coming as 0.0. Is type. Right? 0.02. Now with this, for a measurement of this, I am taking for a measurement of 1 ampere. For measurement of 1 ampere, what is this? So 0.025. 0.025 by 1 into, that is coming as how much? 0.025 by 1 into 100 is calculated. I think 25 by 1000. Yeah, 25 by 1000, 100 gets cancelled. 25, 2.5%. Yes, 2.5, right? 0.025 into 100, so that is coming as as 2.5%. So this error is coming as how much? 0.5. So let us move for the next. So here, fourth instrument, fatafat. Fourth instrument is having guaranteed accuracy of how much? 1%. So guaranteed accuracy error of 1%. So this is 1 by 100 of full scale value, that is 1. So that is 2.0. Okay. So for measurement of, so now we will take for measurement of 1 ampere, what is the limiting error? That is 0.01 divided by, for measurement of 1 ampere, see here the full scale value is a full scale value and this is also for measurement. Definitely what happens? See, 0.01 divided by 100, you are going to get 1% because you are going to almost for the full scale value. For the fourth instrument, the full scale value itself is 1 ampere. So here we are going to get as 1%. So if you see the least error for measurement of 1 ampere, here we are getting a highest error 2.5%, and here we are getting the least error. So fourth instrument is the best suited because the fourth instrument full scale value and your measurement both are matching. So that's why we are going to get the least error. So this is a beautiful question. So the answer goes to the meter 4. Option D is the right answer. D is the right. Meter 4 is the, that is question number. Followed? Yeah. So please remember, books it takes certain time. It takes certain time, but conceptually try to understand. 4 meters are given, their guaranteed accuracy are given. Okay. So each question is a previous year question, and I'm covering the different model questions on error analysis. Every year we are getting a type of question, conceptually same, but conceptually same concept. Either question may be limiting error, guaranteed accuracy error, or meters, voltmeter, ammeter, bridges, some error, but the model, the way of asking the question is. Let us move for one more question. Yeah, question number 6. So if you see this question was asked by IIT Madras in 1997. IIT Madras 1997. In the circuit shown in the figure, for measuring resistance R, if the ammeter indicates 1 ampere, so this is ammeter. So these are resistance we have to measure. This is the unknown. Again, same VI method to measure the resistance. I told you now, to measure the resistance we can use the V by I concept. So here in the circuit shown in the figure, for measuring the resistance R, if the ammeter indicates 1 ampere and the voltmeter indicates 100 volts. So what is the reading indicated? 100. And then the value of R is dash ohms, and the error in the measurement using the ratio V by I is dash %. Two questions are asked in 1990s. First of all, what is the value of R? See, the measured value of R, you can take R is the measured value. Why? Because we are taking the from the meters. MV means measured value. So the measured value of R is what? The voltmeter reading by the ammeter reading. That's it. Voltmeter reading by ammeter reading. What is the voltmeter reading, dear? The voltmeter reading is 100 and the ammeter reading is 1 ampere. So it is going to be 1 ampere now. So it is going to be 100 ohms. So this is the measurement value. So this is the, what is this? This can be taken as measurement value. But what is the true value? To know the true value, let's see the current concept here. So if you think 1 ampere of current is coming here, so this 1 ampere of current is splitting na. Yes, na. So this is splitting in two parts, current passing through the resistor and current passing through voltmeter. But observe, this particular resistance is in parallel to this voltmeter. So the voltage across this resistance and this voltmeter will be same. Yes. So first of all, let us calculate what is a current passing through the voltmeter. So this is the current passing through the voltmeter and this is the current passing through the resistance. But remember, the IV plus IR should be equal to 1 ampere. So to find out the IV, what I can do, so IV is nothing but what? The voltmeter value by the meter resistance RM, the voltmeter resistance RV. So if you take the voltmeter reading is 100 volts and the reading of the resistance is 1000, so it is coming as 0.1 ampere. How much current? It is coming as 0.1 ampere. So this particular thing is 0.1 ampere. So this particular thing is 0.1 ampere. When this is 0.1 ampere, this will be how much? From 1 ampere, 0.1 gone. So this will be how much? 0.9 ampere. Just to the basic electronic circuits. Okay, our networks, current division. Okay, total current is 1 ampere. So current passing through the voltmeter is 0.1 ampere and current passing through the resistor. Current passing through the resistor can be taken as 0.9 amperes. 0.9. So summation of this IV plus IR. So the summation of IV plus IR must be equal. Following up, IV plus IR is equal to 1 ampere. That's it. Now you got IR. Now you can find out the resistance. What is the resistance as per the true value? Yeah. So now if I am taking IR is equal to 0.9 amperes. IR is equal to 0.9 amperes. Is it visible clearly? So IR is equal to 0.9 amperes here. Diagram is getting okay. I will take the next slide. IR is equal to 0.9 amperes. So what is the voltage across a resistor? So let me do here itself. The voltage across a resistor. So if you take the voltage across a resistor, voltage across a resistor is 100 volts. That is can be taken as current passing through the resistor into resistance. Okay, voltage across the resistor is 100 volts. Current passing through the resistor is how much? 0.9 amperes na. Total is 1 ampere na. Total is 1 ampere. 0.9. So I can take it as 0.9 amperes into resistance. So from this, what I can write, the resistance true value I am going to get as 100 by 0.9. 100 by 0.9 means 1000 by 9. So the true value of resistance is how much cutting? 1000 divided by 0.9. Sorry, 1000 divided by 9. It is coming around 111.11. 111.11. So now, which is the true value? Okay, so all of you, this is what finally we got. Our measured value was 100 and our true value is full 1 point. Very, very important question. Why? Because by using the measuring instruments, we are facing the errors. Okay, na? As per the meter readings, we are getting 100 ohms because ammeter is showing 1 ampere, voltmeter is showing 100 volts. So definitely we are going to get 100 ohms. But as per the electronic circuit current division concept, the true value of resistance is coming more extra, 111.11. 1 1. So from this, what is the question asked? In the question he clearly asked, what is the question he asked here? So in the circuit shown in the figure for measuring the resistance, he is asking the value of R is dash ohms. Okay, the value of R is dash ohms. So what you have write here? The value of R kitna hai? So the value of R is 111 point. Please write the true value. Why? Because he is asking the true value, not the indicated value. So the value of R is 111.1 ohms. The answer for the first question. And question asked is the percentage of error. So what is the error? Percentage of error. Percentage of error can be taken as measured value minus true value by true value into, so the measured value is 100, true value is 111.11, true value is 111.11 into 1. Make the calculation. How much you are getting? 100 minus 111.11 divided by 111.11 into 100 is coming as minus 9.9. We have done minus measured value is lesser 0.1 coming minus 9.99. Answer here 9 point following minus. So don't forget, because your true value is bigger. So got it? So these are certain range of. Okay, fine. Now let us go for one more. So this time I have chosen one question from IIT Bombay. If you see this question, 7th question in your, you see the 7th question. Yeah. A current of, please go through, because this particular question is actually related to measuring instruments. Measuring instruments is going to be the upcoming chapter, but in the measuring instruments also we can introduce this error analysis question. That is the beauty of error analysis. Error analysis question can be framed from chapter 1 to chapter last, because errors are present everywhere. There will be errors with respect to instrument level, there will be errors with respect to what you say conceptual level, there will be errors with respect to energy meter, errors with respect to moving iron, dynamometer. Every instrument is having the errors. What is this? A current of how much is shown? Current. So if you see this current, current indication, I think it is the RMS current asking. Okay, a current of 2 plus root 2 sine of 3142 plus 30 degrees. Oh, no problem. Okay, take it. So measured with a thermocouple. Always remember here, thermocouple measures what? Always remember, PMMC measures the DC average value, permanent magnet moving coil measures the average value, whereas a moving iron and thermocouple, they will measure the RMS value. So the IRMS, first of all, I can write IRMS is, okay, so a current of 2 plus root 2 sine term and 2 root 2 cos term is measured with a thermocouple type, 5 amperes, full scale, class 1 meter. The meter reading would lie in the range. First of all, the RMS value. Why? Because thermocouple meters, moving iron meters, true RMS meter, hot wire instruments, these all will measure the RMS value. So what is the RMS for this expression? So RMS expression what? Wherever the DC term is there, we have to take square, and the RMS terms are root 2 by this sine term by root 2 whole square plus, and this is 2 root 2 by root 2. Okay, dear. So now if we check how much we are going to get, this is 2 square 4, root 2 by root 2 1, so 1 square plus 1, root 2 root 2 gets cancelled, 2 square means 4, so 4 plus 4 8 plus 1 root 9, so you are going to get, this is the truth. But actually there is a twist in the question. He has very clearly mentioned 5 amperes full scale class 1 meter. What is this? 5 amperes full scale, 5 amperes full scale, class 1 meter. What is the meaning? Meaning is the full scale value of the meter is 5 ampere. This is clear, sir. But what is this one class? Class 1 means that is the representation in the instrumentation industry. Class 1, class 2, class 3. That 1, 2 represents the guaranteed accuracy error. What it represents? It represents the guaranteed accuracy error. So a percentage of guaranteed accuracy is 1%. That means 5 amperes with plus or minus 1% of scale value. Okay. So now with this, what is the measurement for us? Our measurement is what? 3 amperes. Okay. So the reading that we have to measure is 3 amperes. Now tell me, definitely there is an error in the 3 amperes because there is a guaranteed accuracy error. There is a guaranteed accuracy error when you measure the 5 amperes. So percentage of guaranteed accuracy error is given as how much? 1% of full scale value. So what is that full scale value? 1 by 100 into what is the full scale value? That is 5. So that is coming as 0.0. Now, what is the percentage of limiting error for measurement of how much? 3 amperes. For measurement of 3 amperes, the error will be 0.05 divided by 3 amperes to 100. How much it is? Come plus or minus, if you take 5 by 100, so 5 by 3, I think 5 by 3, it is coming as 1.66 plus or minus 1.6. Understood? So class 1 means having a guaranteed accuracy error of 1%. Try to understand. Class 1 means having a guaranteed accuracy of 1%. 1. Right answer here. 1.63. So how to represent? It is having 3 amperes plus or minus 1.66. Amperes plus or minus 1.66 percentage. So the right answer option C, 3 amperes plus or minus 0.7%. Got it? Very, very good question. Conceptual question. See, different models I'm discussing. Question number. Got it? Please make a note here. Point to be remember here is what? Point to be remember is class 1 meter. Point to be remember is class 1 meter. The class 1 meter is having plus or minus 1% error on the full scale. Yeah. These questions are interesting. They're waiting for this particular question. Question number 8. This question was asked by IIT Kanpur in 1. It was asked by IIT Kanpur 2001. Please see the question. Resistance R1 and R2 have respectively nominal value of 10 ohms and 5 ohms and tolerances of plus or minus 5% and 10%. Okay. So the range of values for the parallel combination of R1 and R2. Very, very interesting. So first of all, what is R1? R1 is 10 ohms with a tolerance of how much? That means what? 10 ohms plus or minus 5%, 5 by 100 of. So that is coming as out 10 ohms plus or minus point. That means the minimum is what? Either 9.5 ohms to 10 point. So this is the R1 range. Got it? This is the R1. Similarly, we can calculate the R2. What is the R2 tolerance? R2 is 5 ohms with a tolerance of 10%. 5 ohms with a tolerance of 10%. That means 5 ohms plus or minus 10 by 100 of 5 ohms. Okay, so that will be 0.5, 5 ohms plus or minus 0.5. Got it? Is it visible clearly? 5 ohms plus or minus 0.5. That means what? What is the R2 value? The R2 value. So R2 value will be, the R2 value will be 5 ohms plus or minus 0.5. అంటే 4.5 to 4.5 ohms to 5.5. 4.5 ohms to 5.5 ohms. These are the values of R1 and R2. Now the question here is asking, when they are connected in parallel, what is the resultant value? We know very clearly we have to take either these two or these. Okay, so now if I am taking these two, minimum is a, so let me take R1 is 9.5 ohms to 10.5 ohms, the minimum. R2 is 4.5 ohms to 5.5, the value. And so what is the R equivalent? R equivalent is equal to R1 R2 by R1 plus R2 for parallel combination. So these two resistors are in parallel. So this is the R1, this is the R2. Cannot take the product of these percentage errors and the summation of the absolute. Why? Because we don't know R1, we know R1 percentage error, we know R2 percentage error, but we don't know as a summation of R1 plus R2. We don't. That's why the better way is to do this like. So the R equivalent will be how much now? Take. So this will be 9.5 into 4.5 by 9.5 plus 5 to 10.5 into 5.5 divided by 10.5 plus. Got it? So how much you are going to get now? Please check it. 9.5 into 4.5 divided by 9.5 plus 4.5, coming around 3.05 ohms to 1. Please use the calci with including the significant figures. Okay, 10.5 into, why? Because sometimes the options are very close, divided by 10.5 plus 5.5, 3.60, 3.609, 0.6. This is the R. This is the best way. Simplest way. 0.05 to 3. Closest answer 2.8, no, 2, no, 3.1. Got it? Got 3.05 to 3.61. So the right answer goes to, option A here. Okay, but remember, when multiple resistors R1, R2, R3 are given, so then we can go for the partial differentiation method. 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So we can go for the partial differentiation. Okay, next question. Okay, please remember, on resistors every year, on resistors parallel combination, every year we are getting the, on resistors every year we are getting the question. Try to understand the series combination and parallel combination. The product of quantities and the summation of quantities we cannot apply in the parallel combination, because when you're taking R1 R2 by R1 plus R2, we don't know what is the percentage error for R1 plus R2. Individually for R1 we may know, individually for R2 we may know, but as a combination of R1 plus R2 we don't. Cannot take the division like that. Okay, chalo, and you will definitely get some error if you do. Now let us move for the one more question. This is the question number 9. Question number 9 is asked by IIT Kharagpur in 2006. Questions are looking lengthy, but Definitely every year, IIT Kharagpur, IIT Kanpur, IIT Chennai, IIT Delhi, every year we are getting one fundamental question on the errors. So never miss the chance to solve the question. All the concepts, or I'm discussing different model. Have you seen different models I'm discussing? So let us see this question. Question number 9. A variable W is related to three other variables x, y, z as W is equal to xy by z. The variables are measured with meters of accuracy plus or minus 0.5% reading plus or minus 1% of full scale value and plus or minus 1.5% of readings respectively. Please have patience. One of the important point in GATE examination that you have to remember is while solving the GATE problems, at least you have to take one or minimum 2 times or 3 times you have to study the problem. He has very clearly given here. He has very clearly mentioned here. Here this particular x, y, z are 3 meters. The resultant is W, and first x meter is having 0.5% of reading as accuracy. Y is having 0.1% plus 1% of full scale value, and the third instrument is having 1.5%. Okay. So first I will do one thing. I will take 3 meters so that it will not be confusing. Take some rate. Just take here 3 meters. I'm taking the 3 meters. This is meter x, y. Okay, x, y. So what is given? First of all, first for x, 0.5% of reading. And remember, the actual readings of the 3 meters are 80, 20, 50, with 100 being the full scale value for all the three. So very clearly given 100 is the full scale value for all. So the full scale value reading is 100 for this, and for y it is 100, and for z is also the full scale value 100. That is the full scale value. Okay, next. And the actual readings are what? 80, 20, 50. The actual readings are 80 x. For x, the reading to be measured is 80, and for y, the reading is 50. For the z, the reading is okay. Now for x, he has given an accuracy in terms of percentage, 0.5% of reading. So for the x, accuracy is what? 0.5% of reading, RDZ, writing RDZ. And for the y, it is 1% of full scale value. So for the y, it is 1% of full scale. And for the z, it is 1.5% of reading. What? 1.5% of. Understood? So now how to get the values? So here we can get the values like this. 0.5% of reading means what? 0.5 by 100 into reading is how much? Okay. So what am I going to get? I'm going to get stage of limiting error. So what is the accuracy we are going to get here? And here 1% of full scale value. 1% of full scale value means 100. Or minus. This is how much? 0.5 into 80 by, it is coming as point plus or minus 0.5. This is 1.5% of reading. That means 0.5 divided by 100. Reading is 50 as 1.5 into 50 divided by coming as point or minus. Okay, so these are the values. This is with respect to now. If you see, these are the percentage, but this is with respect to full scale value. With respect to full scale value 1, now percentage of limiting error for measurement. What? Why? Because this is not with respect to reading, dear. This is not with respect to reading. This is with respect to full scale value. So percentage of limiting error for measurement of what? For measurement of 20 reading. So how much that will be? 20 by that is 5%. So this is coming as plus or minus 5%. That is an error in y. Sorry, y. Yeah. This is coming as x plus or minus 0.4 percentage. And for z, it is coming as plus or minus 0.7. So all the terms we got in terms of the z reading 0.75%. For the instrument y, the error is plus or minus 5%, and the x is 0.4. Got it? So now, what is the next thing he asked? The w. Sorry, the w. So what is the w? W is equal to x into y by z. So this is, if you see, the product of quantities here. Okay, so the product of quantities means what? The percentage in the w is what? In the x, what is the percentage? Plus or minus 0.4%. So for the product of quantities, the percentage errors can be added. So we can take this as plus or minus. We can take this as plus or minus 0.4% plus y is 5% plus, and this is 0.75, because these are product of quantities. For product of quantities, their percentage errors can be added, and that again divided by z. Z is having percentage error. So percentage error in x, percentage error in y. If you add the resultant percentage error, for that again the percentage in z. So how much you are going to get? Percentage of how much? 5.4 plus 5 plus 0.75. We are going to get around 6.1. Somewhere we have done a mistake. Check. .5% of 80. That's correct. 1% of full scale value. Percent. Reading is 25%. I think 1.5%. Oh, I think this is somewhere you've done a mistake. 1.5% of reading. Let's check. I think that should be 1.5% of full scale value. I think it's second 1.5 by 100. So 0.4 plus 5 plus 0.75. 6.15 is coming, but I think 6.15 option is not there. Option C is coming, right? Yeah, 6.15 is coming. Please check this answer. We are getting the 6.5 here. Okay, I think the closest option we are getting here as the option C. Option C we are getting the option, but these C and D very close. 0.5% of the reading, 5% of 80. 4% of real value. Perfect. 6.15, the closest answer is option. The closest answer is option. That is the way. Different meters, different readings. Some meters can be expressed with respect to full scale value, some meters with respect. Okay, so let us move for one more. Yeah, let us go for this question. Let's see this question now. Number 10. IIT Kanpur 2015. IIT Kanpur 2015 का क्वेश्चन. Not here. Okay. So how to solve this question? A capacitive voltage divider is used to measure the bus voltage V bus. So this is the bus voltage. There are two capacitors, nothing but voltage division is not. 1 microfarad. 1 microfarad, this is 9. A capacitive voltage divider is used to measure the bus voltage V bus in a high voltage 50 Hz AC system as shown in the figure. The measurement capacitor, this is the C1 and this is C1 and C2 have tolerances of 10% on their nominal capacitance value. If the bus voltage is 100 kilovolts RMS, so this is 100 kilovolts RMS already. The given is RMS. The maximum RMS output voltage V out is asking. The first, what is a C1? Let me take here. What is a C1? The C1 is 1 microfarad plus or minus 10%. This is 1 microfarad plus or minus 10%. Okay, first let us talk the what is the value. This is 1 microfarad plus or minus 10% means 10 by 100 of 1 micro. That means 1 microfarad plus or minus point means the minimum is 1.9 microfarad to 1.1 micro. Okay, so this is the C1 minimum and this is the C1. Okay, Got it? So these are the values for C. Similarly, try to do for C2. C2 is 9 microfarads plus or minus 10%. C2 is 9 microfarads or minus 10%. So this can be written as 9 microfarads plus or minus 10 by 100 of 9. Okay, this is microfarads. So 90 by 100, that is 0.9. So 9 microfarads or minus 0.9. C2 will be what? 9 minus 0.9, that is 8.1 to 9.9. So this is the C2 minimum and this is C2 maximum. Got it? C2 minimum and C2. Understood? Now the question here is, what is the question asked? Is asking the V out. I think all of you know, when two capacitors are in series, perfectly आपने voltage division rule apply कर सकते ना? When two resistors are in series, the resultant voltage across a particular resistance is equal to that resistance by the total resistance. When two capacitors are in series, the resultant voltage across a particular capacitance will be the opposite capacitance by the total capacitance. So here I can write V out. The voltage across the second capacitor C2 is nothing but C1 opposite capacitance by C1 plus. I think any doubt I can go in detail. I can go in detail that EC people, EE people, IN people, they know voltage division rule. The same current is traveling here. So that is a current passing into XC2. Okay. So what is the current? That is the V supply, V bus divided by Z1, or we can take I into Z2. So this is I into Z2 and this is V supply by Z1 plus Z2 into Z2. So what is Z1? So this is 1 by J omega C1 plus what is Z2? 1 by J omega C2 into what is Z2 here? This is 1 by J omega. So if you go for further simplification, the V out you are going to get as, if you go for further simplification, the V out will be opposite capacitance C1 by the total capacitance C1 plus C2 to supply. That's what the derivation. I think that is a fundamental thing for voltage division rule of the capacitors. The same thing if you are following for the voltage division rule for the resistors, that resistance by the total resistance. Okay, so now got the expression V out is equal to opposite capacitance C1 by into supply, that's it. But the question is having a twist. You see the twist. What is the question? The maximum RMS. What is asking? What is asking? Is asking the maximum RMS. Very, very important here. What they are asking? Asking maximum. The V out should be maximum. But remember, V out is a ratio of two things. V out is a ratio of two things. So you are expecting this as the maxima, means what is the condition? This should be minima and this should be maxima na? Okay, so this should be maxima, this should be minima, means, so what I should write? So C1 maximum divided by C1 and C2 both should be minimum. So this is C1 minimum plus C2 minimum into, got it? So maximum, minimum. Understood? That is a trick in this question. He is asking the maximum output voltage. So the maximum output voltage means the denominator should be lesser. Denominator should be lesser means you should take the minimum capacitor value and numerator must be high. Okay, so now you can substitute what you are going to get. C1 max, C1 max is what? C1 max, here C1 max is this 1.1 and C1 minimum is this, C2 minimum is that, and V bus is already given. So let me here. So understood. So this maximum means this should be minimum. So I can write C1 above. Okay, maximum C1 is 1.1 divided by C1 minimum 0.9 plus C2 minimum. C2 minimum is this 8.1 into bus voltage, that is I think how much, 200 volts, 100 kilovolts, sorry, it is 100 already RMS. Simplify, how much you are going to get? 1.1 divided by 0.9 plus 0.1 into 100. It's coming as 12.22 kilovolts. What you are getting? Very, very good. 12.22. Just he has used the concept of errors, measurements, and he used the concept of network theory. If you're following, he has used the concept of network theory and the, so these are the first. Let us solve this question number 12, then we'll go for question number 11. This question was asked in IIT Roorkee latest 2017 question. What is the question? See, question number 12. The following measurements are obtained on a single phase load. V is 220 volts plus or minus 1%. I is 5 amperes plus or minus 1%. And W is 555 watts plus or minus 2%. Okay, what is this? This is the voltage, this is the current, and this is the power. If the power factor is calculated using these measurements, the worst case error in the calculated power factor in percent is dash. My dear students, all of you know, I think you know the power formula, average power formula given as V into I into cos phi. So this cos phi is the power factor na. So this is the wattmeter P average divided by V into I is the cos phi. So this is nothing but power factor. Question asked here is the percentage error in the power factor. What is asking? What is asking? The percentage in the power factor is asking. So what we can take now? So these are the division and these are the summation. These are the product of quantities. For product of quantities and the division of quantities, what happens? All those percentage errors can be added now. Oh, what I can write here, the percentage error in power factor is equal to percentage error in average power. That means the wattmeter reading plus percentage in voltmeter reading and percentage in current reading. That will be how much, my dear? So this is 2%, this is 1%, this is 1%. Answer is, so exact answer of this question, much. Got it? Very, very beautiful. Okay. Product of quantities and quantities you have to look at. One decimal place, that means 4.0%. So this is the voltage, this is the current. Every year we are getting one question on this model. before, sorry, let us go for this question now. One of the important question. Actually, it is not a question, it is a formula. Directly the formula itself is given in the form of the question. Okay. Two resistors with nominal resistance value R1 and R2 have additive uncertainties delta R1 and delta R2 respectively. The question related to uncertainty. When these resistances are connected in parallel, the standard deviation of the error in the equivalent resistance R is dash. Question asked in 2017. Dear aspirants, for this I want to explain. For example, if you have a expression, one reading W, this W is a function of X, Y, Z. Okay. There is one parameter called W. It is depending on three parameters, X, Y, Z. Okay, X, Y, Z. So it is these are X, Y, Z are independent variables. You know, X, Y, Z are independent variables each other. That means X is not dependent on Y and Y is not dependent on X, like that. They are independent, three independent variables. But in measurement of X, there is uncertainty of Wx. Okay? Error. You understand? You understand? In measurement of X, there is uncertainty. So that is called as Wx. Wy, let us take uncertainty. This is a way of expression of error. Uncertainty in a Y. Uncertainty in a Y. Next, Z. Z is Wz. So this is the uncertainty in a Z. So these all are additive. This uncertainty can be either a standard deviation or it can be a variance, and the error can be expressed in different ways. Normally error is measurement value minus true value, but if you go for mean error, average error, standard deviation, these are what? By taking the history of data, by taking the list of the data, more accuracy, you are going to get more accurate error value, right? Similarly, Wx, if you take it as the uncertainty in X, Wy you take it in the uncertainty in Y, Wy is the uncertainty in Z. Okay. Now, what is the uncertainty in W then? What is the uncertainty in W? Okay. So, this uncertainty in W is given by the uncertainty in W given by one formula, square root of, okay. So, though Wy with respect to independent variable, though X whole square, and what is the uncertainty in X? That is the Wx whole square plus, next, partial differentiation of this W with respect to Y whole square multiplied with uncertainty with Y whole square here. This is rho W by rho Z whole square and the uncertainty in Z. So this is what we call as uncertainty error. Now the important, and W is, see, X is not dependent on Y or Y is not dependent on Z like that, but W is dependent on X, Y, Z. So now error in W will be a part of, error in W will be due to a part of error of X, a part of error of Y, a part of error of Z. That's why the uncertainty in W. You understand? What is this? This is uncertainty. Call this as uncertainty in W. First, that expression W you have to make partial differentiation with respect to X, uncertainty in X we have to take, and that expression W make partial differentiation with respect to Y and uncertainty with Y, that you are going to understand. It is going to be the most accurate error. To represent the error, there are so many methods. Error can be represented generally with a standard deviation, with variance, with a mean, with a average deviation, and last and final, uncertainty. Uncertainty gives you the most accurate error. Now, coming to this question. What is this question? Two resistors with nominal resistance values R1 and R2 have additive uncertainties. There is a R1. Uncertainty in R1 is delta R1. Delta R1 is what? Uncertainty in R1. Next, R2. Uncertainty in R2, delta R2. Uncertainty. Understood? So now this 1 by R is equal to 1 by R1 plus 1 by R2. That is the expression. Now uncertainty in R, how to get it? So uncertainty in R, let us take the uncertainty in R as WR. Uncertainty in R, I want to get it. So first, though R, with respect to R1, partial differentiate it, square of it, and uncertainty in R1, that is delta R1, that whole square. Got it? Expression, partial differentiation with respect to another. Okay. Next, uncertainty with other though R by though R2 whole square, and uncertainty in R2, that is the delta R2 square, and we can take here where this is the expression. Okay, plus or minus. Plus or minus dou R by dou R1 whole square in delta R1 whole square plus dou R by dou R2 whole square in delta R2 whole square. This is the expression. Okay, very important point, my dear. So one of the key topic in the measurement. One of the key topic in the measurement. So which option is matching? Dou R by dou R1, no, square. So this D, so D can be eliminated, C can be eliminated. Dou R by dou R2, this also eliminated. So option A is the understood. Very qualitative question. Okay. See, we started from basic average range of error and we ended at uncertainty. See the different problems. Before closing this particular session, I would like to show how many problems I have. Question number 12 is on uncertainty. Question number 12 is on power factor. Question number 11 is on uncertainty, and this is on voltage division rule. Question number 10. Okay, and we have also discussed the meters reading, and this problem I have to check this closest options are verified as a task. You please verify, and if you find any mistake from my side, you can post in the comment box. Next, question number 8 is given. Question number 7, that is about the thermocouple type and thermocouple type RMS measurement. But here there is one important point: class 1. Class 1. What is the class 1? Class 1 means maintaining 1% guaranteed accuracy. And this is a measurement of resistance by using the VI method. Okay, and this is again the guaranteed accuracy error. The basic precision and one. Okay. So we have taken a list. We have taken a list of questions. Okay. List of questions we have taken on the error analysis. I am suggesting, especially for instrumentation students, you are going to get some questions on error analysis with respect to non-electrical measurement. Sometimes they may give you flow rate measurement. Flow rate formula, Q is equal to area into velocity in a pipe. So there is an error in area measurement, there is an error in velocity measurement. Based on that, they may ask you to find out the, okay na? So, but remember, the concept is same. The error measurement concept is same, but only the measurement is different. It can be measurement of current, measurement of voltage, measurement of resistance, measurement of power, measurement of temperature, measurement of pressure, measurement of pH, measurement of flow rate. Measurements are different, but the concepts, formulas, all are same based on that way. So in the lecture, in the previous lecture, we have discussed a series. In a one shot, we have discussed about the bridges, because in a short span, I want to cover all the topics so that the students can have more awareness. So in the previous lecture, we have discussed in one shot the bridges, DC bridges and AC bridges. And in this lecture, we have discussed in one shot about the different modal problems on error analysis. In the coming lecture, now we will move slowly to the measurement core subject. So as I suggest, as I told already, measurements is a vast subject, but the topics which are coming in the exam regularly, they are very much repetitive. And these model questions, not only for the gate examination, you can also use these model questions for the coming exams like IES, GENCO, TRANSCO, any state level electricity board paper, you can follow this. And remember, especially every state level electricity board, whether it's a Tamil Nadu, Andhra Pradesh, Uttar Pradesh, Uttarakhand, Maharashtra, any state electricity board paper, definitely it contains minimum 8 to 12 questions on the measurements. Because for electrical engineer, for electrical GENCO engineer, the measurement of power, measurement of energy, measurement of resistance, inductance, capacity. So definitely you can use these particular lectures not only for gate and non-gate exams. And never underestimate these particular numerical problems. Different varieties of problems are possible. That is the beauty of measurement subject here. That is the beauty of the measurement subject. In measurement subject, you can merge a problem on bridges, you can merge a problem on analog electronics concept, you can merge a problem from the network theory concept, you can merge a problem from the error analysis related to instrumentation. Different variety of instruments. And each and every instrument, next coming chapter, we are going to start the instruments. Each and every instrument is having constructional features, but don't waste time on much on the constructional features. There, see what is the way I am covering. The same way you prepare, because this is a very short span of time. You're hardly having 2 to 3 months. I think this is November already, December, January, February. In the February first week, you are going to write the gate exam. Hardly you're having 2 months of time. So in this 2 months of time, this particular way of one shot preparation will be very much useful. By using this understanding, you try to solve more problems, it will save your time. And dear aspirants, always maintain a notepad. In the notepad, you try to write the formulas and the different model problems. When this model problem comes like this, what is the methodology we have followed? A short notes or a notepad definitely is going to help you in the upcoming exam. And at the same time, from Gate Wallah, we are conducting mock test. So please try to understand, these mock tests are collectively done with all the faculties together. By taking some time, we have prepared the questions, and these questions definitely will fetch your preparation. So with this, I want to log off this session. First session, we have discussed on the bridges in brief, DC bridges, AC bridges. And this session, we have discussed on error analysis. Coming session, we are going to start measuring instrument. Thank you, one and all.